In this video, we're going to look at a couple of questions with regards to graphing of data. We're going to look at creating a table of values and graphs, including scatter plots with lines of best fit, identifying and describing linear trends, determining whether a relationship is linear or nonlinear, and solving problems involving linear trends and relationships. So the first question here, this is a typical type of multiple choice question you might see. Which of the following graphs shows a positive linear relationship? So remember that a positive linear relationship is one where as one variable increases, so does the other. Well, when it comes to this problem, if we look at number B, as our independent variable, our x variable, which is right here, as this gets larger, our dependent variable, which would be over here, that's getting smaller. It's going down as x gets bigger. So this would not be a positive relationship at all. In C, we have a similar situation. We have as x gets larger, as our independent variable gets larger, our y value, our variable, our dependent variable is also going down. So once again, this is what we call a negative relationship. And in D, this is just completely random. It's completely scattered, and there's no discernible relationship between one variable or the other. So it can't be this one. So I knew that it was A. I skipped by them to show why none of the other ones could work. A is the only one where as my independent variable increases, so does my dependent. And also, I can draw a line to connect all my points. So if I can draw a line, it is linear. So the answer to this question would be A. Okay, here's another question. It's a common type of question you might see with regards to linear relationships. An archer practices shooting at a target at varying distances. Her points are displayed on the table. So we can see that she keeps taking 1 meter back from her starting position. She starts at 18 meters away from the target and moves 1 meter back to 19, 1 meter back from that to 20, and so on and so forth, all the way back until she gets to 25 meters away from the target. And we have her scores here at the bottom. Right? Do the data show a linear relationship or a non-linear relationship? Explain your reasoning. And B, we're going to graph the data. Does the graph support your answer to part A? So we're going to look at each part individually. You may notice that our distance is constantly increasing by 1. We go from 18 to 19, that's an increase of 1. 19 to 20 is an increase of 1. 20 to 21 is an increase of 1. 21 to 22 is an increase of 1. 22 to 23 is an increase of 1. 23 to 24 is an increase of 1. And 24 to 25 is an increase of 1. So every time our distance increases by 1. So that seems to be constant. That's a good thing. Let's compare our scores when we change our distances. If I go from 18 to 19 meters, my score goes up by 1. When I go from 19 to 20 meters, my score goes down by 4, so it's minus 4 from the previous. When I go from 20 to 21 meters, my score goes up by 1. When I go from 7 to 5 meters, my score goes down by 2. When I go from 22 to 23 meters, my score is going down by 3. And when I go from 23 to 24 meters, my score goes up by 1. And finally, from 24 to 25 meters, the score goes down by 3. So there's absolutely no consistency here. So no, this is or I shouldn't say no, this isn't. This is a nonlinear relationship. And the reason is, as distance increases, scores vary. They both increase and decrease. Scores increase and decrease from one position to the next. And they're doing that inconsistently. Okay, so it's a nonlinear relationship. That's what I'm seeing from the data. So we're going to graph it now and compare. So I have my table. I've set up a graph here, and I've made sure that it fit the data that I have. So when the distance is 18 meters, the score is 9. So that would be about right here. At 19 meters, my score is 10, right here. When I'm at 20 meters, my score is down to 6. When my score is, when my distance is 21 meters, my score is up to 7. When my distance is 22, my score is down to 5 now. At 23 meters, it's all the way down to 2. At 24 meters, it's back up to 3. And at 25 meters, it's down to 0. So we can see my data, if I were to connect my dots, my data would kind of travel in a zigzag pattern. It's not very linear. So it does support my answer. There is one thing here, though. It does have a somewhat of a trend downwards. If I can draw a line of best fit, it does appear that my data is following a somewhat of a linear trend, but it is a nonlinear trend. There is some correlation to a linear trend, but it's not exactly linear. It does go up and down, so it kind of zigzags down the grid. So to summarize this unit again, or this section, we can graph a scatter plot of the data in a table of values to view the trend in the data. We can determine if there's a linear or nonlinear trend. Using technology, or our best guess, if we don't have technology available, we can create a line of best fit, like I just did, to show how well a scatter plot fits or does not fit a linear trend. A linear trend can be positive, where both the independent and dependent variables increase, or it can be negative, where the dependent variable decreases when the independent variable increases. And finally, often it does not make sense in the context of the problem to connect the data with a line, although it may be done for analysis purposes. There are situations where it doesn't make sense at all to have your line connected or your dots connected because they could deal with single physical objects. We can't have, in a lot of cases, half an object. For instance, we can't count half people. And it's situations like that where we wouldn't be able to connect our dots.